Okay, hello. So, in in today's class, we will look a little more on a couple of useful data structures, namely stacks and queues. So you can think of this as a nice extension to the object-oriented topic which we covered in the previous lecture. So I'll mm, represent one of them as an object, and you can have a look at it. So it serves as a good example. But not just that, these two data structures, namely stacks and queues, are important in their own right because they have specific properties which make them useful for many applications, and that's quite a large variety of applications. And it is also used in several algorithms. To implement various algorithms, you might need the behavior produced by these two data structures. So in that sense, these are useful, and it is important for you to be aware of them. So, so stacks and queues are the two data structures which we will see, and they are dynamic data structures. Dynamic in the sense the contents of those two structures, of these data structures, will change based on what you insert and what you delete from them. And the important characteristic which I mentioned is that the insert and delete operations are pre-specified. So unlike a list, for example, a list is also a dynamic data structure where you can keep on adding or removing or modifying things. Like you've seen several examples of lists. Also an NumPy array for that matter. But for example, stacks and queues are something built on top of lists, which kind of restrict how or which control how data is input and output from these two data structures. So we will see exactly soon. So in fact, stack provides what is known as LIFO, or last in first out operation, and queue provides what is known as FIFO, or first in first out. So what they are will be apparent in the next couple of slides. So this is an example of a stack. So I have pictorially represented a stack here. So stack is like this, like you must have seen a stack of plates in a restaurant or in your mess. You have not come to the mess, but yeah, there is a stack of plates in a mess, right? So it's currently here the stack is empty, and the stack is created, and currently it is empty. So there are two basic operations in a stack. First operation is push. Push means you are inserting an element into a stack. So we are pushing A into the stack. So now A goes into the stack. So whatever is the topmost element of the stack, that is represented by top. Top means, top is, so you can think of top as a pointer or a reference to the topmost element of the stack. So this stack currently has only A, and so the top of this stack is A. So I've not said what is A. A could be anything. So A could be a variable, it could be an object, it could be whatever it is that you want. I'm just illustrating the operation of a stack. Okay, so now I've pushed A, so my stack is like this. Then I've pushed B, so B is pushed on top of A. So now the new top is B. B becomes the new top. Now the stack has two elements. The second operation in the stack is a pop. So pop always removes the topmost element of the stack. So when I pop the stack, this particular stack, B is the top, so B is returned by the stack, and now the top is updated to A. A becomes the top. And if I do one more pop operation, A also comes out and the stack becomes empty. So this is the basic operation of a stack. So this is why it says LIFO, that is last in first out. So whatever was in the last is going to come out first. Fine. So this is how a stack operates. So I've kind of abstracted it here, but this is illustrating how the operation of a stack takes place. So the basic operations are push and pop. So let's see how I can create a stack. So I've created, let's say, an object called stack, and I'm going to push three numbers into it. For example, s2 is my stack. s2.push is s2.push1. So I'm pushing 1 onto the stack, pushing 2, and I'm pushing 3. So these 3 things are pushed onto my stack, which is called S2 now. So I've created a stack object. Okay, so there is a class called a stack, and I've created an object of that class, and I've done these operations on that object. Then I want to print the stack, so I do print of S2, print S2. So I want to represent the stack in a nice way so that you know what is the top. So that's what I've done here. So print stack star. So the stack, see the stack contained 1, 2 and 3. So this is 1, 2 and 3, and the star indicates what is the top. So 3 is the most recently pushed element, so that is the top. So 3 is the top. So I have my print statement or my print function is doing this for me. Okay, and I want my print statement to give me a stack which I can nicely see. So that is why the top is also displayed in this print. Now I pop. So what should get popped? 3 should get popped. So 3 is returned by the stack. And now if I print the stack again, now since 3 is returned, now 2 becomes the top. The contents of the stack is 1 and 2. So this is the stack after popping. Fine. So this is how I have created the stack. So this stack is a class which I created now. So see a little bit about implementation details. Python by default, Python lists for example, already provide a default behavior as a stack. So Python lists, the built-in list object already has methods which will facilitate you to use the list as a stack. Fine. So I can use that. That is fine. But what I've done here is I have created my own class which is called a stack, which I've called a stack, which is built on top of the list. So I am not implementing the stack operations from scratch. I am reusing what is there in the list, but I have created what is known as a wrapper class around that list so that the stack which is so produced is more suitable for my purpose. Okay, so for example, I wanted some custom methods which will be nice to have. That's what I thought. So that is why I created this custom made class called a stack. So it will become clear once I show you the code. So for example, so this is the code which I created. So this is my class stack. So I need a constructor that is init. So you can see that there is an attribute called contents. So this is the list which essentially which holds actually the data of the stack. Fine. Now in the previous slide, I had this print method which printed the stack nicely. It also showed me the contents of the stack, and it also showed me which is the top. So I implemented that method here. So you can see that it is a dunder method. So str. So basically what I'm doing is I'm printing out the contents, that list, whatever is there in the stack, that attribute, which is basically a list. I put it into a string, and then I have added a star appended a star to the last element, because the last element in this list is going to be my top. So I have printed it in the way I want. Then I need a method called push, so which is the operation to add an element to a stack. That is what I've done here. So basically what I've done is here I've used the built-in list method append. So if I was not using this custom class, stack class, if I just want to use a list as a stack, I should keep using append method to do the push operation. So what I've done is I've created a wrapper method around that method, around the append method, so that I want to call my method as push. I don't want to call it append. So I'm more familiar with it, for example. So I call this, I define this method push, and internally it called append. Then I also have a pop. So the built-in list already has a method called pop, which will do this for me. So I'm just calling that method from inside my pop. And then I have another method called peek, which I thought is a good method for a stack to have. So basically peek, what does it do is it returns me the topmost element without actually popping the element. So it's just like peeking over somebody's shoulder, right? So I just want to know what is the top without popping the stack. So that is the peek method, and it returns the last element of the stack of this list which contains the stack. So I have a small main program which will do this, and so I have created the stack, I pushed Monday, Tuesday, I printed, I have popped out, and I'm printing out whatever is popped. So Monday and Tuesday gets popped out, the stack is now going to be empty. Then I've pushed January, March, and Friday. So I've got 3 elements in the stack, and I want to see what is on top. So I do dot peek, and I'm printing what is peaked, and I'm also printing out the stack. So you can see the output here. Right? So I popped Tuesday and Monday. This is the output of the peak because I've pushed in January, March, and Friday. So Friday is the top now, and this is the contents of the stack now. Okay, so this method, so what I've done here, like I said, is I've used a wrapper class. So I have defined this stack class, which is a wrapper class, which is more like a convenience class, which builds on top of another existing class. So here it is important to realize that I do not want to use a subclass. I mean, like, one more way to do this is, if you remember what we said about subclasses, we can also extend. I can also extend the list class and make a new subclass out of it. But subclass is not really needed here, because for my purpose, I just wanted the facilities, all the functionality which I want is already there in list. So, and I just want to make it available in a more convenient way. I'm not adding any new functionality. The only additional functionality I'm adding is I'm just manipulating whatever is already there in the list. So it did not require me to extend the list class. So that is why I did not extend. Fine. So so please do go through the code. You can understand what I've done here. Okay. Now, now a stack can have what is known as an overflow and an underflow. An overflow happens when you are pushing onto a stack which is already full, that is overflowing. And underflow means you're trying to pop from an empty stack. So these are special conditions, which are usually error conditions. So you can, if you want more features in this stack, you can think of implementing an overflow and underflow. Okay, so this is for you to think. Since I'm using a list here in the stack, Python lists grow as needed. But how will you implement overflow in the stack defined in the previous slide? So that is one exercise which you can think of, how to implement overflow. Underflow is still easy, because at some point the list, if you keep popping, the list will become empty, and then if you try to pop again, it results in a underflow. But overflow in a Python list is a little unheard of. It's a little uncommon, because Python lists keep growing as you need. Whereas in languages like C, that need not be the case. When you define a list or an array, the size of the array is fixed. Usually it is fixed. So you can think about how to do it. If you are interested, you can even implement underflow and overflow in this class, in this stack class. So you can maybe throw a particular kind of exception if the underflow or overflow happens. So you can have a try catch block which will catch this exception. So one of these methods, push and pop, the pop and push, can when you check, you can put them inside try catch block, and when underflow or overflow happens, you can raise an appropriate exception and throw it back to the main program if you want. That's up to you how to handle it. Right? So these are design decisions which you can think based on what is the application you want to do. You can also do this homework. So you can implement some additional methods onto this stack class. You can implement a method isEmpty. So isEmpty is a method which returns true if the stack is empty. Otherwise it returns false. Then you can implement length. Length will tell you how many elements are there in the stack. So this is a built-in function, so you can use a dunder method to implement length. Then you can have another method called isOnTop, and it takes an argument x. So isOnTop, what it does is it returns true if x is on top of the stack, and it returns false if x is not on the top of the stack. Okay, so you can implement these methods as a homework, and you can add these methods to this stack class, that you can take it up as a homework. Now let us see a couple of examples of applications of stacks. You must have seen undo in text editors whenever you're typing something in MS Word or some editor like that. Suppose you're typing something, you typed a word, then you added an image, then you added a table. Now you want to undo it. So when you do undo, Control Z, when you do undo, usually, I mean, what will happen is the last done action is going to be removed first. So in this case, the table will be removed. If you do undo again, then the image will be removed. If you do undo again, then the text, whatever you typed, will be removed. So this is naturally an operation for a stack. So in a text editor, every action you do is put into a stack to implement the undo operation. So that is an example. Like I said, the stacks have use in lots of algorithms. For example, many graph algorithms internally use stacks to implement various operations, depth first search, breadth first search, etc. So many of these algorithms will use a stack. Yet another very important use of a stack is to handle function calls. So again, I will not go into details here. I will give you only a very simple example. Now, for example, see this code which I showed you when we were checking scope. When we were talking about scope, we had shown this code snippet. So there is my main program, which calls a function f, and inside f, this is my f. There's some statement. Then f calls g. Now this is g. There's some statements. G calls h. This is h. Fine. So now when you run this program, first this assignment happens, then you call f, you come to f, this assignment happens, you call g, then you go to g, you do this assignment, then you call h, you go to h. After this statement is executed, then you have to come back. This function is over, h is over, h only has one statement. So where will you come back to? Should you come back to main? Should you come back to g? Should you come back to f? Right? So this is where a stack will be useful. So what you should do is, after you finish h, you must come back to what called h. So in this case, the most previously called function was g. And after that is also over, you should go back to f. So again, there's naturally a stack coming into the picture. So that I will just illustrate it by this stack here. So for example, so whenever a function call happens, in the processor, there is usually a register known as a program counter, PC. Okay. Again, I will not get into details here, but you just think of a PC as a special register in the CPU, in the processor, which will hold the address of the next instruction. So this program is in memory. If you want to run this program, it is somewhere in the main memory of the computer. And every instruction of this program is stored in a particular memory location. And that memory location will have an address. The program counter, the PC register, keeps track of what is the next address, keeps track of the address of the next instruction to be executed. So for example, once you start the main program, x3, we started from here. So the program counter, when you are in this statement, when you are executing this statement, the program counter will have the address of this instruction, because you are going to run this statement next. Then it detects that f is a function call. Okay, so once you start executing f, the program counter will actually now contain the next statement, which is line number 23, the address of line number 23. So, but now since this is a function call, the control has to be transferred to the function. So what it does is, the program counter stores into a stack. So here it is, main 23. So this is not how it is done, but I'm just illustrating the stack here, where this is telling me which is the function and which is the line which has to go to next. So this is in some sense the content of the program counter. So once you see a function call, the current program counter is pushed onto a stack, and then control is transferred to that particular function. So the address of that function is fetched. So then it goes here. So now the program counter now becomes line number 9, execute 5. Then the next, once this line is executed, it goes to this line. The program counter becomes 11. Now this is a function call. So now if you start this function call, you must return to this function. So again, you push this value into a stack. So that's what I've done here, F11. So this is the value of the program counter, which is going to be stored into a stack before you call the function G. And then so on, the same process repeats. Then from G you come here. So this is the first line. When you reach this function call, the program counter of G has to be stored into the stack. So this is actually the line number 16. So I'm just storing it as line number 16. But of course the function ends here. So once you come to line number 16, we'll realize that the function ends. And then you come to H, you execute H. Once H is over, how do you go back to? Where should you go back to? You should go back to pop out the element from the stack and go to that particular memory location and execute the memory location in this, execute the instruction in this memory location. So you come back to G16, then you realize that the function is over. So now G is also over, so pop out that. So the next one will be F11, so it comes back to F11. Then that means G is also complete, and then you come to, you finish this statement, then you come out, and this one is finally popped, and then you come back here. Okay, so I have kind of simplified it here. Because there are very many more things which get stored onto a stack whenever there's a function call. But you can keep this in mind. One of the things to be stored is that of the program counter, because after executing a function, you must know where to come back. Fine. So this is a simple application and a very important application of a stack. It is more important even when you have recursive functions. There also you must know, right? So for whenever there is any type of function call, always a stack is involved. So that was about stacks. The other data structure is that of a queue. So a queue looks like this. Let me illustrate how a queue looks like. Okay, just drink some water. Recording is going on, right? Okay. So we are looking at queues now. A queue behaves differently from a stack. So again, let's assume that we're going to implement a queue using a list. A queue has a different kind of behavior. There are two things in a queue. There is a front and there is a rear. You always enter from the rear and you exit from the front. That is typically a queue you see in a bus stop, right? When new people come to the queue, they come to the end of the queue. So you always add elements from the rear and you delete elements from the front. So for example, this is, let's say the queue is empty. The operation is known as enqueue. So let's say I enqueue A. So I'm putting A onto the queue. Then I'm enqueuing B. So B comes to the queue. And I'm enqueuing C. So C comes to the queue. So it's like adding at the end, right? We keep on adding at the end. Now I do the other operation is known as dequeue. So when I do dequeue, the frontmost element comes out. So A is returned. So in this queue, which contains A, B, C, the frontmost portion is A. So A is returned, and now B becomes the new front. This is the front now. Fine, and now if you dequeue again, then B will come out. Then if you dequeue once again, then C will come out. So the queue provides what is first in, first out behavior. Whatever goes in first will come out first, because that is the objective of a queue. Now there are some implementational detail here. So I kept saying that we keep adding to the rear of the queue. So you may be wondering why I did not add the A here. Okay, that is how you implement. That is up to you. I mean, so in this case, I have used, if this were a list, I have used this kind of append function of a list. If I were using append function, this is how the list would get appended. So, but the problem, if you see here, is now suppose you enqueue, see how many elements are there in this list, which I'm going to use as a queue. I have 1, 2, 3, 4, 5, 6 elements are there. I have enqueued A. So A comes here. Now how many elements are left? I have space to insert 5 more elements. 3, 4, 5. Then I enqueue B, then I enqueue C. So I have space now to insert 3 more elements because the size of my queue is 6. Then suppose I dequeue. So I remove A is removed. So actually now how many places are left in the queue? There is actually 1, 2, 3, 4. 4 empty places are there in the queue actually. But because based on how you implement it, if you are counting whatever is the last element of the queue minus the length of the queue, then you will actually assume that there are only 3 elements to be 3 spaces available when actually there are 4 spaces available. So these are implementation details. Okay, so if you are implementing this in a language like C, for example, you have to worry about these details. But Python makes things easier for us. So to rather than directly using a list, which we could do in this case of stack, it is not very efficient to use a list, a standard list to implement the queue because of this problem. Because basically what should happen is after you dequeue an element, then you must push these elements to the front so that the remaining spaces are available for the queue to be filled up. Okay, so ideally speaking, after you dequeue, you must move all these elements one step to the left so that the first element of the queue is always the front. Fine. So this will make the implementation easy. So, but rather than directly using a list to do this, we will use a built-in function or a built-in class in Python from the collections module. So there is a collections.deq. This is called DEQUE. It's not DQ. It is pronounced as deq. Now the funny thing about deq is that deq is not just a queue. A deq is a generalized data structure which can implement both stack as well as a queue. So the collections.deq is a class which implements both stacks and queues. It has lots of methods. You can go to the documentation and see what are the methods it provides. It provides several methods. It includes methods which will make the deq act as a stack, or it can also, at the same time, it also provides methods by which the deq can act as a queue. Okay, so you can, if you want a stack as well as a queue, you can create one object collections deq as a stack, and collections deq, if you want a queue, you can create collections deq, a new object as a queue, and then you can do basically, you can do the corresponding operations on the objects queue and the stack, which are instances of the class collections deq. So for example, how to use it: if you want to use a queue, if you want to use deq as a queue, so you can create dequeue queue and I've appended 2 strings. So append is a method you use to enqueue, and then pop left method is what you use to pop from the left. That means it is like dequeue. This dequeue operation which you see here is implemented as pop left function in the class collections.deq. Okay, so if you want details, please look at the documentation. It provides you lots of methods for and examples of how to use deq. Okay, so I hope you understood the fundamental behavior of stack and queue and how you can implement it in Python. So if you want a customized stack, you can of course write your own stack, which I wrote here. Or if you don't want to use, you can just use the list method. You can use a standard list as a Python stack by using the append and the pop methods. Also, you have another option. You can also use the collections.deq, which is a generalized data structure which can be used to both implement both stacks as well as queues. What are applications of queues? For example, job scheduling in an operating system. So this is a very important application, one of the most common applications of a queue, because your computer, basically the standard computer which you use, is running multiple programs at the same time, right? You're opening a browser and you're also opening a Word document, you're also typing code in Python. All those things are happening, but you have only one processor. So what the operating system is doing is it is time switching the processor between all these various applications which are running at the same time. And since it is done very fast, you tend to think that all the operations are running at the same time. Actually it is not. Since there is only one CPU, each of them is time shared. Each of the applications is time shared by the CPU, by time shared by the operating system. The various applications time shares the CPU, and this is done by by an operating system is implementing actually a queue. Okay, so first, if your Word is getting the processor, Word gets the processor, then browser gets the processor, and after Word finishes the processor, it is put back into the queue so that it goes in round robin fashion. Another application is again in various algorithms, and for example, various graph algorithms also use a queue. A queue can be used to process items in a particular order. Fine, so that is a quick introduction to stack and queue. Please go through the code, implement this, I think some questions on stacks are going to be asked in lab 10. So please have an idea of stack and do go through stacks and queues. Do go through the code. As always, if you have any queries, please post it on Slack, or you can send me an email or send me a message. Okay. Thank you, everyone.